Hi guys, so let's continue the B module and today we are doing a very important topic called as time, speed and distance. So there are multiple parts to this. One of them is the basic ideas and the concept of average speed. Then there is a new concept that we are supposed to explore which is relative speed. And the third part that we are supposed to see is the questions based on trains and boats and streams. So the first part, as usual, the basic formula of speed that we all know since school days, that speed is equal to distance upon time. Speed is equal to distance upon time. Now based on this formula, we can derive some relations. The first one of them is that speed is directly proportional to distance, provided the third one, that is time is constant, and speed is inversely proportional to time, provided the third one, which is distance in this case, is constant. And it makes a lot of logical sense to realize all these things as well, because we know that if you increase the speed, distance covered is also more. If we decrease the speed, distance covered is also less. Similarly, if we increase the speed, we will reach the destination earlier. That means time taken to complete the distance is less. So that means speed and time are inversely proportional. Now using these relationships, we can figure out some ratios. The first one of them is, if speed changes in the ratio a is to b, then time taken to cover the same distance changes in what ratio, and we know already that speed and time are inversely proportional. तो if speed का ratio is a is to b, time का ratio हो जाएगा उसका inverse, यानी हो जाएगा b is to a. Then distance covered in the same time changes in what ratio? So speed and distance are directly proportional. So जो भी ratio speed का होगा वही ratio distance का भी होगा. So distance का ratio also is a is to b only. Now some standard conversions that we would be requiring for problem solving. First one of them is how to go from kilometer per hour to meter per second. So 1 kilometer per hour to 1 meter per second, if you want to convert, we will always multiply by 5 by 18. This 5 by 18, how we arrive at that? So you literally convert. So from kilometer to meter. So 1 kilometer is 1000 meters, and per hour, so we'll have to divide 1 hour to second. So 1 hour is 3600 second. So 1000 upon 3600, after reducing you get 5 by 18. So basically, if you want to convert from kilometer per hour, you have to always multiply by 5 by 18 as a multiplying factor to convert into meter per second. If you want to do ulta, meter per second से kilometer per hour में जाना है, obviously the multiplying factor reverses. We have to multiply by 18 by 5. And lastly, 1 mile per hour. So 1 mile is usually 1.6 kilometers. So 1 mile per hour becomes 1.6 kilometer per hour. So these will be requiring in some of the questions as far as the conversion is concerned. The second type from this first part is average speed. It's a very simple topic. First of all, when does the average speed come into the picture? So obviously when you cover different journeys at different speeds. For example, suppose, as you all can see, there are 3 different journeys that you all can see. First part of the journey is a flat road. So suppose vehicle covers that distance d1 at some random speed s1. Then there is a bridge coming up, so vehicle might slow down a bit. Suppose vehicle covers that distance d2 in some different speed s2. And then there is a bumpy road, so speed might vary again. So let's assume vehicle covers that distance d3 at some random speed s3. So if someone comes and asks me that what is the average speed for this entire journey, so there is only one formula that you are supposed to remember as far as average speed is concerned, which is total distance upon total time. No other formula is there for average speed. Standalone formula, always remember that, total distance upon total time. Now in this particular example, obviously total distance, we can easily just add all the 3 individual distance d1, d2, d3. We will have the total distance, and total time they have not given, but you know the formula for speed, which is distance upon time. So time becomes distance upon speed, and for all the individual journeys we have the distances, we have the speeds. So all we have to do is just divide the individual distances with their respective speeds so as to get the individual times. So when we do d1 upon s1, we'll get the time t1 for the first journey. We do d2 upon s2, we get time t2 for the second journey. And we do d3 upon s3, we get time for the third journey. And t1 plus t2 plus t3 will give me the total time. So for this particular example, this is something that we had to do, but the broader idea remains the same. Only one formula, total distance upon total time. Remember that, don't deviate from that. That is the only formula for average speed. Now what else that they can switch it up here is, instead of giving you the distances, they might give you the speed and the times. So denominator is sorted, total time, but for finding out the speeds, you will have to again use the basic formula of speed, which is distance upon time, and so on. The second part of this particular topic is relative speed, and as the name itself suggests, that it's not an absolute value, it's compared basically. And when does relative speed come into the picture? Again, when two of the objects, both of them have their individual speeds in the picture. So relative speed, when it comes in the picture, when two or more objects move together, and that means one of the object speed is in relation to that of the other object. When both the objects have their own individual speed, that's when relative speed comes into the picture. Then there is one or two odd theory points that you should straight away remember in this particular scenario. When the objects, both the objects which has their own individual speeds, when both of them are running in the same direction. If the objects are running in the same direction, what you are supposed to remember is that relative speed is the difference of both the speeds. Whenever objects are running in the same direction, relative speed is the difference of both the speeds. And obviously vice versa, whenever objects are running in the opposite direction, relative speed is the sum of both the speeds. Whenever objects are running in the same direction, relative speed is the sum of both the speeds. That's the two pointers that you should remember. Apart from that, there is a simple formula for relative speed that you can also remember, which is time taken to meet / cross. It is the same formula. Why meet / cross? Because if the objects are moving in the opposite direction, then they will meet. If they are moving in the same direction, then one of the objects will cross the other object, and hence the formula is same. So time taken to meet / cross is given by a formula, generic formula you should remember, which is separation upon relative speed. This is the another formula that you are supposed to remember. Actually, this is not a very different formula, because we already know that speed is equal to distance upon time. So time becomes distance upon speed, and here the distance between the two objects is in a way fancily called as separation between the two objects. And then relative speed will have by default two sub scenarios as it is, whether objects are moving in the same direction or whether they are moving in the different direction. If they move in the same direction, you have to subtract that s1 minus s2. If they move in the opposite direction, you're supposed to add them. We get s1 plus s2. So this is how the concept of relative speed works out, and this will take us to the next part, which is questions based on train. So trains is entirely all about relative speeds, and there are scenarios that we need to explore as far as the trains are concerned. Now, one good thing about trains is that the questions are very, very straightforward and very, very simple and easy. So you don't have to again complicate a lot of things unnecessarily. You just stick to the basics, and you will sail through very easily. So let's do the scenarios. The first of the scenario, time taken to cross a stationary object. Time taken to cross a stationary object with a negligible width. Example, a train is crossing a man pole or a tree which is standing at the ground. So one good thing here that we easily observe that the object is a stationary object. It is not moving. So that means it does not have its own speed. And if it does not have its own speed, that means relative speed is gone off already, because that means only train will be the one object that will be having the speed. The object is stationary. The second good thing about this is that it has negligible width. Now, these are the types of scenarios that you need to remember the formula and then apply whenever you come across them in the questions. So negligible width, the only length which is under consideration is the length of the train. So if this is the scenario, time taken to cross a stationary object of a negligible width, a man, pole, or a tree standing, then the formula for time taken to meet slash cross is again given by a term which is length of the train upon speed of the train. So what you can remember is formula is LT upon ST. Length of the train upon speed of the train. LT upon ST. First scenario, very straightforward, no relative speed, object is stationary and it has negligible width also. LT upon ST. The second scenario, slightly improved, time taken to cross a stationary object of a substantial width. Example, a train is crossing a platform or a bridge. Now, what do we do in that particular case is, first of all, again, the object is stationary object. Okay. So again, what we are going to have is whatever is the platform or the bridge is there. Now we cannot ignore the length of that particular platform or bridge. It is there as usual. So we cannot ignore that anymore. But the object is still stationary only. And in that case, again, relative speed is not there. But in that case, the formula is the train has to cover both the distances, the length of the train as well as the length of the platform, and hence the distance covered becomes, the numerator part of the formula becomes LT upon WO, where WO is apparently the width of the object. So LT plus WO, which is width of the object plus length of the train. Again, object is stationary, so the only speed which is under consideration is the speed of the train. So that remains as it is. So the second scenario, substantial width but stationary object, LT plus WO upon ST. So these are the first two scenarios which are very simple, very easy because the objects are stationary. So relative speed is not there. Now I hope on a similar background you can think of two more additional scenarios where objects will have its own speed. One category with negligible width and one category with substantial width. And then as usual, relative speed will by default has their two own separate cases, whether objects are running in the same direction or whether they are moving in a different direction. So based on that, try to think of those scenarios also if you can, and try to have the formulae also in place for those scenarios. The next part of this topic is basically boats and streams, and as usual, boat will have its own speed and hence it is measured under a condition called as still water. Water is not moving and that is the actual speed of the boat. And then there is water flowing beneath the boats also, which will also have its own speed. So first of all, we need to define the term very clearly. So we'll define speed of the stream or speed of the water as b, small b, and speed of the boat in still water. Look at the language, it is defined in still water is defined as small a. And then there are as usual two scenarios that we need to explore. One is upstream and one is downstream. Now what do I mean by downstream is that water helps you to move ahead, and obviously if you have rowed or if you have had a swim or had gone for a swim or something, that you would realize that water easily helps you to move ahead. You don't have to take any extra efforts, and that is what is downstream condition. With the flow, water assists you, so your effective speed is more, and hence downstream speed is addition of both the speed of the boat plus speed of the water. Whereas the second scenario, which is upstream, obviously it is against the flow. Against the flow, it will be very, very difficult to row forward. You'll have to work very, very harder, and obviously water will not help you. It will try to resist you as much as possible. So that means upstream speed becomes a minus b. Your effective speed reduces. So these are the two scenarios: upstream speed and downstream speed, with the flow, against the flow. Now sometimes what happens is, that examiner don't give you A and B separately, but they will give you the values of upstream speed and downstream speed, and from there, using these two linear equations, you should be able to figure out the values of A and B. So for finding out A, you'll have to add the two equations and you get the value as SD plus SU upon 2. And for B, obviously you will have to subtract. So B in terms of upstream and downstream speed is SD minus SU upon 2. So you should remember these things also, because you never know which type of data you will have with you for solving the question. So A in terms of upstream and downstream is addition of both divided by 2. B in terms of upstream and downstream is subtraction of both divided by 2. So this is both sense streams for you. Now how you should ideally interchange between the scenarios is that if you observe trains, that means basically relative speed wale scenario, at that time we said that same direction we should subtract, opposite direction we should add. Here it is exactly the ulta. Here in the same direction we add and in the opposite direction we subtract. So you understand very clearly that trains or relative speed is opposite of boats and streams. The next small part which is similar to boats and streams that you can explore is obviously escalator, and we all have been through this either in malls or now these days at railway stations also. So escalators, it's a moving stairway, moving up or moving down stairway. Suppose escalator is moving up, you are also going up. You know the experience, very simple, very straightforward. All you have to do is just go and stand there. It will automatically take you up. You don't have to take any efforts at all. That means escalator is going in the same direction. You are also going in the same direction. That can be treated as downstream direction with the flow. Similarly, suppose escalator goes up, you are going down. Please don't try that, but you know that it will be very, very difficult to pass through this. And obviously you realize that this is going to be an upstream condition against the flow. So again, you should not remember anything extra as such for escalator, because you exactly know that it is as same as boats and streams. So all the ideas can be applied here with some bits of modification and works. So trains, boats and speeds, and escalator, three are different scenarios. You should not bother or worry about remembering everything at once. You should be smart enough to figure out how to interchange between the topics using the main ideas. The last part, one small note that exactly what the differences between the relative speed and boats and streams. One of them is that relative speed, the frame of reference is same. Now what do I mean by that is, somebody who's suppose sitting inside the train and somebody who's watching it from outside, for them the effect will be the same, and that is why it is said that the frame of reference is same in the relative speed, which is basically trains, whereas in boats and streams the frame of reference is not same, and that is a major difference between the both of them. So that's it guys, as far as the concepts are concerned. If you have any queries, please go through this one more time and do let us know, and we will be happy to answer your questions. So thank you so much. Have a great day.